In this video, we will be presenting the principles behind an aeroplane's hugely successful ability to climb. In straight and level flight, lift, drag, thrust and weight are all balanced. What you see here is of course a simplified representation of the main forces that are in equilibrium. In a steady climb, the aeroplane is also in the state of equilibrium. Thrust and drag act in line with the relative airflow along the aeroplane's flight path, whereas lift acts at right angle to the relative airflow. Weight acts down towards the centre of the Earth. The common misconception is that lift increases in a climb. In a steady climb, where the forces are in equilibrium, a component of weight points backwards. So weight may be resolved into two vectors: the weight component that opposes lift and the rear weight component. Lift is slightly reduced because the opposing weight component is also reduced at the expense of the rear weight component. The rear weight component acts in the same direction as drag, therefore it contributes to drag. So to maintain the equilibrium and steady climb, thrust must increase. This is called excess thrust. Are you still not convinced that lift is smaller in a climb? Imagine that this aeroplane is capable of climbing at the ultimate 90-degree angle of climb. Now you can see how it becomes about the excess thrust, not lift. An aeroplane will achieve its best angle of climb when excess thrust is the greatest. This curve represents thrust available against airspeed for straight and level flight. The faster you wish to fly, the less effective the propeller is, so the less thrust it's able to generate. The thrust required curve suggests that generally you need more thrust if you wish to fly faster. Comparing the two curves, the greatest difference between the thrust required and thrust available is the maximum excess thrust, which happens to be your best angle of climb airspeed.